In this video, we are going to look at Theorem 10.1, properties of elements under homomorphisms. And since homomorphisms are generalizations of isomorphisms, then they still retain a lot of the same properties that we already know are true for isomorphisms, but not all of them. So let's have a look at the different properties that we still have. So first of all, number one, a homomorphism, phi, carries the identity of G to the identity of G bar. So just as with isomorphisms, this is still true with homomorphisms. Number two, phi of G to the n is phi of G quantity to the n for all n in Z. That is also still true. We already had that for isomorphisms and we still have it for homomorphisms. Now 3 is a little bit different. For isomorphisms, we had that the order of G and the order of phi of G had to be exactly the same for an isomorphism. That doesn't have to be the case anymore. So now we only know that if the order of G is finite, then the order of phi of G is going to divide the order of G. So we don't have equality anymore, but we still have that the order of phi of G has to divide the order of G. And then number 4 is new. We are now talking about the kernel of V, and the kernel of V has to be a subgroup of G. And number 5, if phi of G is equal to G prime, then the inverse image of G prime is all the elements in G that have the same image. So all the x in G such that phi of x is equal to G prime, that is exactly the left coset G kernel phi. And we've seen several examples of that in example 3, A and B. We saw that the inverse images of particular elements were the entire cosets of something that mapped to an element in G bar. All right, I just want to prove one of these properties. So since 1 and 2, we already have proven them for isomorphisms. It's still true here. 3, you can see in the notes. 5, we've already seen some illustrations, and 4, I actually want to prove real quick. So let's prove just property 4, that the kernel of phi is a subgroup of G. And we're going to use the one-step subgroup test. And so we're going to assume that we already know properties 1, 2, and 3. Actually, we'll only need 1 and 2. But by property 1, we know that phi carries the identity of G to the identity of G bar. So since phi of E is equal to E bar, we already have something that's in the kernel. So the identity is in the kernel of phi, and so therefore kernel phi is not empty. That was the first thing that we have to show for the one-step subgroup test. And then the second thing that we have to show is that if we have two things, A and B, in the kernel, we need to show that A, B inverse is also in the kernel. That was the second thing that we have to show, the main step in the one-step subgroup test. All right, so let's see. So we have A and B in kernel phi. What does it mean? Well, it means that phi of A is equal to phi of B is equal to the identity in G bar, E bar. Okay, so let's see what we get if we are looking at phi of A B inverse. We want to show that that is also that AB inverse is in the kernel, and so that means we have to show that phi of AB inverse is equal to the identity in G bar as well. So this is what we want to show right here. So this is the to show part. So let's see, what's phi of AB inverse? Since we have a homomorphism, that's phi of A, phi of B inverse. But what is that? I'm going to just copy down phi of A because I want to deal with phi of B inverse. Well, phi of B inverse is phi of B inverse. That's by property 2 that we already had. And so now phi of A, well, A is in the kernel, so phi of A is E bar. And then phi of B is also E bar, so we have E bar inverse, but E bar inverse is the identity itself. So that is just the identity in G bar, E bar. And so that shows that A, B inverse is in the kernel of phi. And so we've shown that the kernel of phi is a subgroup of G.